sense, illuminate, connect.
Hello, my name is Jamshed Namdar Khan. I'm Factory Applications Engineer for optocouplers at Avago Technologies. The objective of today's presentation is to compare and contrast different isolation technologies for galvanic isolation and to determine if there are any significant differences between the different galvanic isolation technologies. We want to determine and demonstrate what differentiates the various galvanic isolation technologies available to the designers for their insulation and isolation requirements. We want to establish if the isolation capabilities of each device are equivalent or not. If their insulation and isolation capabilities are not equivalent, then we want to know which isolation technologies offers a robust insulation capability and which isolation technology lacks in robustness and which may be hazardous in a harsh industrial environment applications. Different type of isolators that are available in the industry today are: number one, optocouplers, also known as opto-isolators; number two, magnetically coupled micro-machine transformer-based isolators; number three, capacitively coupled isolators; number four, radio frequency or RF-based isolators. We will determine through appropriate criteria or evaluation techniques how good is the galvanic isolation provided or promised by each of the indicated competing isolation technologies. Insulation levels are defined by various safety standards such as IEC 60664 or VDE 110 or EN 50178. There are primarily 4 insulation levels and are classified as follows. Number one, basic insulation. This is the insulation needed to provide basic protection against electrical shock between a part at hazardous voltage and earth-hit ground. Number two, supplementary insulation is an independent insulation applied in addition to basic insulation in order to ensure protection against electrical shock in the event of a failure of basic insulation. Number three, double insulation is an insulation comprising both basic insulation and supplementary insulation. Number four, reinforced insulation is a single insulation system which provides a degree of protection against electric shock equivalent to double insulation. A basic insulation is considered to be shorted under a single fault condition and thus cannot be considered fail-safe. In contrast, reinforced insulation provides 2 levels of protection, making it fail-safe and allowing user access. Unlike basic or supplementary insulation, a single reinforced insulation system does not imply that the insulation must be one homogeneous piece. It may comprise several layers which cannot be tested singly as basic or supplementary insulations. Various equipment standards further define requirements for reinforced insulation. For example, the medical standard IEC 60601-1 edition 3 defines the requirements for reinforced insulation as follows. A. Reinforced insulation must have a distance through insulation, also known as DTI, or internal clearance of at least 0.4 millimeters. B. At least 2 layers of material, each of which will pass the appropriate dielectric test, or C. 3 layers of materials for which all combinations of 2 layers together will pass the appropriate dielectric strength tests. Let us take a look at how optocouplers are constructed. Optocoupler construction in general consists of top, under, or vertical alignment scheme where the emitter or LED is separated from the detector through some distance through insulation distance. This distance through insulation for a Avago optocoupler ranges in dimension from a minimum of 80 micrometers to a maximum of 1 millimeter. In addition, the dielectric insulation layers are generally 3 layers. A very high breakdown insulation tape material consisting of Kapton tape is sandwiched between layers of another high dielectric insulation material, which is silicone, on either side of the Kapton tape. Therefore, for Avago optocouplers, these will meet the criteria for reinforced insulation based either on meeting the 0.4 millimeter distance through insulation criteria or through meeting the 2 or 3 layer insulation material criteria that will meet the dielectric test criteria for reinforced insulation. Now let us take a look at the competing isolation technologies such as magnetic or capacitive isolators and take a look at their distance through insulation dimensions and also take a look at the number of insulation layers that define the internal clearance. It turns out that the internal clearance or distance through insulation for magnetic and capacitive isolators ranges from 8 micrometers to 17 micrometers. In addition, the number of insulation layers are only 1. This means that the magnetic and capacitive isolators fail to meet the criteria for reinforced insulation on both counts. Number 1, magnetic and capacitive isolators cannot be classified as reinforced insulation because they do not have a minimum of 0.4 millimeter distance through insulation. Number 2, magnetic and capacitive isolators cannot be classified as reinforced insulation because their insulation layer is a single insulation layer and not 2 layers or 3 layers of insulation that must pass the relevant dielectric insulation test. The IC 60747-5-5 is the International Component Level Safety Standard for optocouplers. This standard evaluates the insulation level capability of the optocoupler component through rigorous testing that includes preconditioning and then a slew of environmental tests. At the type testing stage, the environmental test consists of temperature cycling, shock, vibration, accelerated dry heat, accelerated damp heat, storage temperature tests, and steady state damp heat consisting of 85 degrees relative humidity and 85 degrees C for 21 days. The climatic classification of the optocoupler component is based on this environmental testing. The final measurements expose the optocoupler to working voltage partial discharge testing tested at 1.6 times the working voltage specification with a very stringent partial discharge limit of 5 picocoulombs. In addition, the components go through surge tests. This surge test consists of exposure to 50 discharges of 10 kilovolts with a maximum discharge rate of 12 discharges per minute. These final measurements also include dielectric strength tests and isolation resistance tests. Additional component level testing during the type testing includes identifying and characterization for the maximum input and output safety limiting values. The maximum input and output safety limiting values are the maximum power that can be applied at the input or the output side of an isolation device under a single fault condition under which the insulation integrity of the isolator will still be intact. The designers need to be aware that external safety components will need to be implemented by design such that the safety limiting values are not exceeded under an electrical fault condition. Finally, the type testing also includes measurements of external creepage and clearance numbers for the optocoupler component. Another point that needs to be stressed here is that only a component level safety standard that addresses the component level insulation integrity testing can only effectively evaluate the insulation integrity of an isolator. The component level safety standard determines the failure modes and activation energies associated with the relevant insulation. That is, a component level standard contains the appropriate requirements for a particular isolator. The biggest shortcoming with the competing isolation technologies is that they do not yet have a component level standard that properly evaluates their insulation integrity and failure modes. Just obtaining certification to equipment level standards is not the right approach, as the equipment level safety standards do not contain requirements for properly evaluating or specifying the insulation capabilities of the various isolators. Let us say the optocouplers and magnetic and capacitive isolators are exposed to the same basic environmental tests such as temperature cycling, vibration and shock, and followed by dielectric strength tests such as 1-minute V-isolation test. For evaluation purposes, the basic environmental and dielectric strength tests that both the optocouplers or the magnetic or capacitive isolators were exposed to are as follows. Number 1, rapid change of temperature or temperature cycling. Number 2, vibration. Number 3, shock. Number 4, dielectric strength tests such as V-isolation tests of 3.75 kilovolts RMS or 5 kilovolts RMS per minute. It is found that at the basic environmental testing and dielectric strength testing, both the optocouplers pass the defined and relevant tests, and so do the competing technologies isolators such as magnetic or capacitive isolators. So far, so good. Both the optocouplers and competing technologies isolators appear to have similar capabilities, and no big problems or differences were detected or found. Now let's take a look at surge test capability of optocouplers, magnetic isolators, and capacitive isolators. Surge test is a safety requirement for any isolating device to ensure that they can survive voltage surge of up to 10 kilovolts peak. Safety protection for reinforced insulation is required in industrial and medical applications to protect end users and patients from high voltage transients. It is defined in IEC 60747-5-5, IEC 61000-4-5, and VDE 0884-10, which is a standard for digital isolators. Test is done by shorting all the input pins and all the output pins of the isolation device. A high voltage source is connected to the shorted pins, and the return path is to the shorted output pins. The test voltage is a 10 kilovolt transient pulse with a fast rise time of 1.2 microseconds and a fall or decay time of 50 microseconds. Test voltage starts from lower predetermined voltage and increased at predetermined step intervals until the device fails, and that will determine the surge voltage capability of the device under test. Resistivity is measured after each voltage interval to determine if the device passed or failed. Device will pass if its input to output resistivity is 10 gigaohms at 500 volts input to output isolation voltage. The result shows that the optocoupler reached up to 20 kilovolts of voltage surge. The high voltage surge capability of optocouplers is attributed to having thick distance through insulation, which is typically around 400 micrometers. Thicker insulation, like those of optocouplers, is more resistant to breakdowns because of the reduced electric field stress. Electric field stress is inversely proportional to distance through insulation, which means that the higher the DTI is, the lower is the electric field stress between the input and output conductors. The next device, a magnetic isolator, have a surge test capability of 10 kilovolts. Like optocoupler, it also passed the surge test, but its capability is limited to 10 kilovolts only and will fail at 12 kilovolts. The last device, a capacitive isolator, have a surge test capability of 6 kilovolts, which means that it failed the surge test and cannot be certified for reinforced insulation. It is also to be noted that under UL 1577, double protection isolators, that is for reinforced insulation, require a surge test of 20 kilovolts peak. This means that the alternative isolators cannot meet reinforced insulation requirements not only under the IEC 60747-5-5, but also do not meet the reinforced insulation criteria under the UL 1577 standard. Accelerated life test is a critical reliability test to determine any weakness in the insulation of an isolation device. The data from this test can also be used to predict the life expectancy of an isolation device at a particular working voltage. In this in-house experiment, optocouplers, magnetic isolators, and capacitive isolators are subjected to high voltage and high temperature to accelerate its time to failure. All of the isolation devices used in this test are in SOIC 16 package with creepage of 8 millimeters. They are tested in an air circulating oven with temperature of 125 degrees Celsius and 1.6 kilovolts RMS voltage, and is applied continuously to the shorted input and shorted output pins of the isolation device. 1.6 kilovolts RMS is chosen based on solid insulation capability of 200 volts RMS per millimeters. So a device with 8 millimeters of creepage has an intrinsic breakdown capability of 1.6 kilovolts RMS. The leakage current is constantly measured, and an alarm sounds when the current meter detects more than 100 microamps of leakage. When breakdown scenario occurs, test is halted, and the device under test are bench measured for leakage current for fault identification. Test results show that optocouplers did not fail up to 4,000 hours in which the test is halted. Two different part numbers of magnetic isolators failed at 14 hours and 12 hours respectively, and the capacitive isolator failed at 21 hours of accelerated life test. Both magnetic isolators and capacitive isolators have comparatively low time to failure compared to an optocoupler. The comparatively low DTI of magnetic and capacitive isolators means that their input and output conductors experience a much higher electric field stress, which eventually leads to breakdown of its insulation barrier. Optocouplers, however, have a much thicker distance through insulation and experience a significantly lower electric field stress between its input and output conductors. Partial discharge test is a widely recognized test in determining the dielectric strength capability of an isolation device. It is defined in several equipment and component standards such as IEC 60664, IEC 61800, EN 50718, IEC 60747-5-5, and VDE 0884. Partial discharge test determines the homogeneous quality and impurity of insulation material in an isolation device. In this test, a device is subjected to a predetermined high voltage, and the partial discharge or corona discharge, which is quantified in picocoulomb unit, is measured by a special equipment for partial discharge test. The Pearson criterion is a partial discharge measurement of less than 5 picocoulombs. Any presence of partial discharge of more than 5 picocoulombs is considered a failure. In this experiment, we used SO16 isolation devices with predetermined working voltage capability of 1.6 kilovolts V sub RMS based on the 8 millimeter creepage and 200 volts per millimeter capability. The 1.6 kilovolts RMS working voltage capability is multiplied by 1.875 times and gives a partial discharge voltage of 3 kilovolts RMS. So the predetermined voltage of 3 kilovolts RMS is used in the routine or production partial discharge test for 1 second. The test results show that optocouplers, magnetic isolators, and capacitive isolators all pass the partial discharge test. This partial discharge test result is important as it guarantees the working voltage specification of an isolation device. However, if you compare the partial discharge test with the accelerated life test result, there is an inconsistency that questions the effectiveness of partial discharge test for each of the different isolation devices. Now, let's examine this one by one. For optocouplers, it passed the 3 kilovolts RMS partial discharge test and shows no degradation by passing up to 4,000 hours in the accelerated life test. This shows that partial discharge test is an effective method in predicting the life expectancy of an optocoupler. For the magnetic isolator, it also passed the 3 kilovolts RMS partial discharge test. However, based on the thermodynamic model they used for life expectancy prediction, it must have a time to failure of 80 hours. Its actual time to failure in accelerated life test is only 12 hours, and the other part number to be only 14 hours, which is significantly lower than the 80 hours times to failure prediction. This means the partial discharge test may not be an effective test in predicting the life expectancy of a magnetic device. And for the capacitive isolator, it also passed the 3 kilovolts RMS partial discharge test. However, based on the TDDB or time-dependent dielectric breakdown / electric field model they use for life expectancy prediction, it must have a time to failure of 2,500 hours. Its actual time to failure in accelerated life test is only 21 hours, which is also significantly lower than the 2,500 hours times to failure prediction. This also means that partial discharge test may not be an effective test in predicting the life expectancy of a capacitive device. This study shows that partial discharge test is effective in predicting life expectancy of an optocoupler. However, more study needs to be done to determine if partial discharge test is also effective for alternative isolators such as magnetic and capacitive isolators. We must now summarize the significant weaknesses of the magnetic and capacitive isolators compared to optocouplers or optoisolators. Number one of the biggest weaknesses of the magnetic and capacitive isolators is that they do not have a component level safety standard. A component level safety standard is essential to evaluate the insulation based on their activation energies and relevant failure modes. Number two, the distance through insulation of the magnetic and capacitive isolators is much smaller compared to optocouplers, and at least 1/4 to 1/10 smaller than for optocouplers. This smaller internal clearance imposes a much higher electric field strength and is the root cause for the abysmal surge capability, low ESD capability, and low working voltage capability. Number 3, the magnetic and capacitive isolators do not meet the two key criteria for reinforced insulation. A, they do not have a minimum DTI of 0.4 millimeter. B, their insulation layers consist of only one layer, not two insulation layers or three insulation layers. Number 4, both the IC 60747-5-5 standard and the UL 1577 standard require surge testing of 10 kilovolts peak or 20 kilovolts peak, and the magnetic and capacitive isolators do not meet the required surge testing capability. Number 5, the magnetic and capacitive isolators do not pass accelerated life testing and fail within 12 to 21 hours of the accelerated life test. Number 6, partial discharge test is seen not to provide a correlation between accelerated life test and partial discharge test. This means that partial discharge testing is not the correct predictor or the correct test for magnetic or capacitive isolators. In conclusion, it can be safely predicted that the optocoupler is still the best choice for reinforced insulation applications. Optocouplers have been around for over 30 years, and their insulation breakdown has never been a problem. Optocouplers are certified to reinforced insulation levels, whereas the alternative technologies are granted only basic insulation levels. The magnetic isolators and capacitive isolators may never survive in harsh industrial environments where high surges, high ESD levels, and high working voltages are the norm.